Hi folks, today I bring you another clock project based on a single integrated circuit solution, driving a dual LED display. This design appeared in electronic books from the late 1970s, more specifically around 1978 and 1979. So, in many ways, this device is truly a dinosaur from National Semiconductor. The integrated circuit used here is the MM5455N. These chips could commonly be found in standalone clocks or in bedside clock radios from that era. Like the other vintage clock solutions we already explored on this channel, this one also supports the selection between 50 Hz and 60 Hz operation. To control the display segments, the circuit uses a technique based on half-wave rectification from each transformer winding. In our test setup, we used a transformer with 2 times 7.5 volts AC. At this point, I must reinforce an important safety warning. Extreme care must always be taken when working with main voltage, because it is extremely dangerous and can result in serious injury or even death. Internally, the integrated circuit uses a phase shift method to control the display segments. Because of this, the circuit becomes sensitive to the introduction of an isolation capacitor in series with the 100 kΩ resistor used for the 50 and 60 Hz input. Adding that capacitor introduces additional phase shift, which causes some segments to become partially illuminated. For that reason, we ended up using only the resistor. I would also like to highlight an interesting detail about the display used in this solution. The display only supports the 12-hour format. It does not include the segments A, D, E, F, and G. The display itself had to be repaired because segments B and C were damaged. To restore them, we installed 2 red SMD LEDs, which were simply the components available at the time directly onto the PCB pads. Since all the printed circuit traces and external connection points already exist, it would actually be possible to add LEDs to the remaining segments as well. That would allow the creation of the Digit 2, making the display capable of supporting a 24-hour format. The button control method used by this chip is somewhat unusual. Each pin can behave either as a negative input or a positive input, depending on which other button is pressed at the same time. Because of this, I strongly recommend paying close attention to the current limiting resistors, which are suggested to be around 1 kΩ. An error is the implementation can easily create a short circuit in the power supply when 2 buttons are pressed simultaneously. In this project, we only implemented 3 buttons: set time, fast, and slow. However, the logic used for these buttons is exactly the same for the remaining functions. The integrated circuit uses a standard 2.54mm pin spacing, which allows direct installation on a breadboard together with the display. This type of LED display can also be easily replaced by a custom construction using 2, 3, or even more low-consumption LEDs in series per segment. That allows the creation of displays with much larger dimensions. To do that correctly, we only need to adjust the anode limiting resistors. As expected in this kind of design, where the LEDs use series resistors, we can observe some variation in segment brightness during digit transitions. This happens because the total load changes dynamically, affecting the current flowing through the display resistors. Since the display polarization uses different electrical phases, the segments actually turn on and off at the frequency of the main supply. In this case, that frequency is 50 Hz. The camera captures this effect as a visible flicker on the LEDs. However, to the naked eye, human vision is generally not sensitive to that switching frequency. Finally, I would also highlight the importance of carefully matching the connection order between the integrated circuit and the display itself. As you can see, bringing this vintage clock back to life is actually extremely simple.